Imagine this is a quark. It would be roughly the size of this tennis ball here, but in reality it would be scaled down by a factor of 15 quadrillion. You wouldn't be able to see it if you tried, and people have tried. Along with another particle, the gluon, these form the theory of quantum chromodynamics, also known as QCD. Here, let me explain. In QCD, quarks and gluons are always part of a group of two or more quarks, known as hadrons. This is due to two effects: asymptotic freedom, proven by David Gross, Frank Wilczek, and David Pulitzer, and confinement, not yet proven but greatly suggested by years of experiments. To describe these properties, imagine you have two quarks, with a rubber band gluon tube connecting them. As you start to pull, it's fairly easy, but then, as the quarks get farther and farther apart, you need more and more energy to pull until it snaps. That is when a lot of energy is released. Yet how that energy is released differs from our world and the quantum world. In our world, the energy releases in the form of sound energy. But in the quantum world, there's a lot more energy. So when the gluon tube snaps, the energy transforms into matter itself, creating two new antimatter quarks out of thin air. These newly created antiquarks then pair with the quarks that just snapped apart. This is what asymptotic freedom and confinement are. Asymptotic freedom shows that the farther the quarks are from each other, the harder it is to break them apart. And according to confinement, if you do break them apart, two quark pairs spontaneously appear from the energy. So these properties guarantee that quarks can never be without a pair, and therefore are always in a group of two or more. In addition to these properties, we also know QCD causes a state of matter hotter than plasma to occur. This state of matter is known as quark-gluon plasma, or quark matter, and it is created when plasma exists in a very hot and pressurized environment. In this environment, the hadrons lose the gluons which hold them together and turn into a sort of soup of quarks and gluons. We haven't ever actually observed natural quark matter, but we have created it. On February 10th, 2000, particle physicists at CERN, a lab in Switzerland, carried out an experiment in which they artificially created quark matter. Sadly, it's very difficult to keep this state of matter stable in our environment, so this experiment didn't tell us any of the properties of quark matter. Instead, it just proved its existence. We currently believe that quark matter can only exist naturally inside the second most extreme environment in the universe, neutron stars. Now, the fundamental question here is, why does any of this matter? How do asymptotic freedom, confinement, and quark matter help us better understand our world? Well, as it turns out, by studying QCD, we will be able to understand what our universe was like in its very early stages. And once we understand the past, we will be able to understand the present.